Bismillahirrahmanirrahim. Assalamu alaikum students. We are going to discuss another problem today. So let me write the problem, then we will discuss the solution together. So today's problem goes like this. Plastic rod whose length L is 220 centimeters and whose radius R is 3.6 millimeters, carries a negative charge Q of magnitude 3.8 into 10 raised power minus 7 coulomb, spread uniformly over its surface what is the electric field near the midpoint of the rod at a point on its surface. This is our today's problem. So before going to the solution, let me check it first. A plastic rod whose length L is 220 centimeter and whose radius R is 3.6 millimeters carries a negative charge Q of magnitude 3.8 into 10 raised power minus 7 coulomb. So L is length, R is radius, Q is the magnitude of charge on it, spread uniformly over its surface. What is the electric field near the midpoint of the rod at a point on its surface? Right? So before going to the solution, let me refresh your memory. If I have infinite line of charge, so I have some infinite line of charge. For example, it can be positively charged, it can be negatively charged, right? When I say I have infinite line of charge, That means it is infinite in extent. You can not find its ends. It is infinite on both sides, right? So it will have some linear charge density. Let lambda be its linear charge density. Linear charge density means charge per unit length available on the line. Its unit will be coulomb per meter. And if we assume lambda is constant, that means lambda is throughout same. And if we take a point P, r distance from the line, then the magnitude of electric field at point P is lambda by 2 pi epsilon naught r. I repeat, if I have an infinite line of charge with constant linear charge density lambda, and I take point P, r distance from the line, the electric field at point P, let me write it EP, is lambda by 2 pi epsilon naught r. We're assuming that this line is placed in vacuum. You know epsilon naught is permittivity of free space. And the electric field will be outward perpendicular to the line. For this case, because it is positively charged line. If it is negatively charged line, then electric field will be inward, right? So let us move now to our problem. In our case, we have a line. Let me use some color, different color. I have a line which is not infinite in extent, but is finite. It has certain length, and that length is 220 centimeters, right? And it is negatively charged. Let me show charge on it. It is negatively charged. Negative charge is on it. It has radius, which is given to us. Its radius is 3.6 millimeters, right? It carries a negative charge, and that negative charge on it has magnitude, which is given to us. Q is 3.8 into 10 raised power minus 7 coulomb. 3.8 into 10 raised power minus 7 coulomb is Q. Charge is negative, that means electric field will be inward, perpendicular to the line, this way. Now we are asked to find, and it is given that charge is spread uniformly over a surface. That means lambda is constant. Linear charge density is constant. Now we are asked to find electric field near the midpoint of the rod. That means at this point, P is the midpoint of the rod. Near the midpoint of the rod, at a point on its surface, right? We have to find electric field at this point. Now, one thing we know that electric field at this point is going to be inward because the rod is negatively charged. We want to find its magnitude, right? For that, first we find the linear charge density. Q charge is distributed over length uniformly. So it is Q by L. Q is minus because the charge is negative. 3.8 into 10 raised power minus 7 coulomb over a length just to 20 centimeter. That means it is 2.2 meter. Converted it into meters. So my lambda is minus 3.8 into 10 raised power minus 7 coulomb over length of the rod 2.2 meter. When I calculate it, check it, it turns out to be minus 1.73 into 10 raised power minus 7 coulomb per meter. It's my lambda. Let me encircle it. As always, check the calculation at home. So we have calculated the linear charge density on the rod, which is minus 1.73 into 10 raised by minus 7 coulomb per meter. The question is, can we use this expression to find the electric field or not? Right? The justification is, if our point of observation is on the surface and it is away from the ends, as is the case here, our point is on the surface of the rod. I think I should show you the radius of the rod in the figure. Let me write the figure this way, or I will show it here. I have to find the electric field near the midpoint of the rod. That means this much distance will be 110 centimeters. 110 centimeter, 110 centimeter, because overall length is 220 centimeters, right? So it is 110, 110. And my point of observation is on the surface of the rod. It is said that at a point on its surface, right? So for this point of observation, I am away from the ends, I am at the midpoint, and I am close enough to the rod. I am on its surface. So for this point, even if the rod is finite in extent, but for this point, it is approximately infinite in extent. I repeat, my point of observation lies on the surface of the rod, so it is close to the rod, and it is away from the ends because it is at the midpoint. So for this point, this finite rod will appear as infinite rod. So I can make use of this expression. It will be a good approximation. So we can use the electric field of our infinite rod for finite rods as well if our point of observation is away from the ends and close to the rod, as is the situation here. So when I am on the surface, what is my R? My R is the radius, because I'm from the center of the rod. Situation is like this. This is my rod. I am at the surface, at the center of the rod, and this is my radius. Let me use this color, black. This is R. So my distance from the center, which is R here, my small r is R, radius of the rod. So let us put the numbers and solve for the electric field at point P. So my EP is lambda by 2 pi epsilon naught R is my capital R. Small r is my capital R, radius of the rod. So let us put the numbers. My lambda is minus 1.73 into 10 raised power minus 7 coulomb per meter, minus 1.73 into 10 raised power minus 7 coulomb per meter. We have calculated it. Then I have 2 pi times the value of epsilon naught is 8.85 into 10 raised power minus 12 coulomb square per Newton meter square. Then I have R, which is radius, which is 0.0036 meter. You can see it is 3.6 millimeter. That means it is 3.6 into 10 raised power minus 3 meter, right? Because 1 millimeter is 10 raised power minus 3 meter. That means it is 0.0036 meter. 0.0036 meter. So we have substituted for it 0.0036 meter. Epsilon naught is 8.85 10 raised power minus 12 coulomb square per Newton meter square. When we put the numbers, the electric field at the given point turns out to be minus 8.6 into 10 raised power 5 Newton per coulomb. Minus 8.6 into 10 raised power 5 Newton per coulomb. Check the calculation at home. So we have found the electric field. The minus sign tells us that, as I have already told you, because the rod is negatively charged, the direction of the electric field is radially inward toward the axis of the rod. As we have shown, this electric field will be toward the rod, right? As I have shown here. You can see how we make use of the expressions for infinite charge distributions, for finite charge distributions as well, for suitable points of observation. I hope you are enjoying these problems. So this is all for today. Don't forget to like, share, and subscribe my channel. You can give comment in the comment box. Thank you. God bless you. Assalamu alaikum.